करो।
It's showing.
देखते हैं।
Okay, is it visible?
Yes, it is.
Okay, so I will start.
बस नीचे ये स्क्वायर सा कुछ दिख रहा है जिसमें
अच्छा,
तुमने
ये
हाथ
साइड
फैला
में,
रखा है।
साइड में,
हाँ
हाँ.
बस ठीक है, अब चला गया।
Okay, so good evening. Today I am going to talk about electron microscopy, which is a very good technique to characterize our sample and to know more about our sample to the atomic size. So this is the part one. In part one, I will give a basic fundamental ideas about microscopy and what type of microscopy we can use in a practical way. In the second part, I will talk about the instrumentation, and the third part, I will talk about different type of detectors, the analysis, because in some type of microscopy, the straightforward images you cannot do, so analysis is required. So today I am talking about the basic concept and the basic fundamental things about the microscopy. So electron microscopy is very good if we are trying to know our material down to the atomic size. So till 19th century, or we can say till 1920, 30, we were having good visible light microscopes. But the problem with the visible light microscope was we were very limited for the wavelength of the light which we can use. It means we can select anything from violet to the red. So if we take a very common laser green light and we use that wavelength, so still we can maximum go to the resolution of 300 nanometer. But if you are doing the SEM or TEM and you want to know about your sample and about their instrument also, you should have some prerequisite knowledge about your crystallography, how diffraction is happening of the electron beam and image contrast, what is giving you the different contrast in your sample. That's what meaning. Elastic scattering, inelastic scattering event means basic physics. You should know the fundamentals of spectroscopy. And whatever is happening inside the instrument and what is happening during the interaction with your sample, everything is based on the physics laws. Nothing is beyond that. So we can divide our microscopy into two parts. One is TEM and one is SEM. One is scanning electron microscopy and one is transmission electron microscopy. I will tell both what is the difference between them. First, we will compare it with the visible light microscopy and the electron microscopy. If we see the fundamental symmetric diagram, we will see the parts are same, the individual sections are same. We need a light source, we need a source in both microscopy. We need condenser lenses. In case of visible light microscopy, we have optical lenses. In case of electron sources, electron microscopy, we need magnetic condenser lenses. They will align the electron beam. In case of objective lenses, light source have optic lenses, they have electric and magnetic objective lenses. So everything, components are different, but the steps are same. The screens are different in both, even the projector lenses are different, sources are different, but the concept is approximately same. So why do we need electrons? Why we went towards electrons from the light source? Because the image resolution in the VLM is very limited. And what is the image resolution? Image resolution means, imagine there are two lines very side by side, and your eyes, they can see these lines separately. This is image resolution. How far you can go beyond the limit that you can see very close lines individual. That is image resolution. So if you are taking a visible light microscopy, if you take a green light laser, you can only see a 2 points which are close to 300 nanometer. Beyond that, you cannot go with the help of VLM. So it all started when de Broglie gave idea about the duality, that wave particle duality of the electrons. Then Davidson and Germer and Thomson and Reed independently they carried out those experiment and proved that electrons have wave nature. That's a very fundamental things. That's not going to do anything in the instrument, but how it started. If we don't know the wave particle nature of the electrons, we cannot go directly to the electron microscopy. That's why. But the electron microscope in the practical structure is still a controversial thing. Knoll and Ruska, they are considered as the inventor of the electron microscope because they patented their instrument in 1932. But at the same time, there was one more group which was working in a private company, Siemens, which is very famous company now. And they also actually made the same instrument with having some more capability, but their patent was a little bit late, but in the same year, 1932, both of the groups have patented, but Knoll and Ruska, they are known as the inventor. So that is the fundamental difference. Why do we need electron microscopy? Because when we use electrons, we can accelerate our electrons and we can change the wavelength in a very wide range. And it can go to a atomic size. It means 0.1 nanometer or 1 angstrom we can go. So if we are watching something directly from our eye, we can only able to resolve 0.1 to 0.2 mm. That's what our image resolution is. Our retina can only resolve this distance. So now, what is the depth of field and depth of focus for a microscope? That I will tell. Means depth of field means if you are seeing a picture, if everything is in focus, it means the depth of field is very large. If a very small
Nikhil,
portion is in focus, then it is called a very small depth of field. Depth of
Nikhil, can I ask
focus,
a question?
yes, sir.
So you said that the resolution of human eye is 1.1 millimeter.
Yeah, 0.1 to 0.2 millimeter. Yes, sir.
Okay. Okay. So is it because of the wavelength that our eyes are sensitive to? So
Yes, sir.
if we had looked, let's say in UV, so if our eyes were capable of looking or watching things in the UV range, then we could have resolved better.
Means the limitations is because of that also. Means we can see only the visible range through our eyes. That's also one reason. And moreover, we have a particular magnification of our eye. Like if we compare with the optical cameras now, then we can compare if we are having a 50 mm lens, then it has the same magnification as our eye. So our eye cannot magnify after a particular image. It means you see, we always say that if we are going beyond 7 inch or 6 inch, we cannot focus. Similarly, we cannot zoom something beyond a scope.
Okay.
So visible range is also a reason. And another reason is magnification. See, in light microscope, we are using light source only. But because of lenses, we are maximizing it. We are
Oh, yes.
magnifying
True.
our image.
True.
So there is a two reasons. Means we can only see in visible range. Moreover, our eye cannot magnify more than something because different creatures have different magnifications. They don't see in the same aspect ratio as our eye see.
So both things play role. So the
Both things,
first reason.
yes, both things play a role. Our magnification of the eye, that limit, and as well as we can only see the visible range.
Okay.
So with the help of one picture, I will try to convey. So this is a picture with a very big depth of field. That's why you are able to see everything clearly. The far behind that logo also and the very close that pole also you can see very clearly. But if you see in the second picture, only the flower is in the focus. The background is blurred. The background is not in the focus. It means the depth of field is very low for that picture. So depth of field and depends on the image location, and depth of focus depends on the sensor or your source, the camera. Now, if we see the real picture of the VLM, that's how a visible light microscope looks in the real picture. And this is the picture of a scanning electron microscope of a GS Gemini instrument. If we see very closely, sorry. These are different detectors. You are seeing these are different detectors. This is actually camera, sample holder, which we can keep inside and outside. So what happens? You can create the vacuum in the chamber, and separately you can take out the sample, you can close the chamber, so you vacuum, you need not to do again and again. So the system is having a complicated structure inside, but these three are the different detectors I will talk about later, that they can detect different type of electron in our sample if they are interacting with the sample. So how does electron interact with the matter? When we take a very high energy electron beam, it will fall on the sample, and after falling, many different mechanism will happen inside the sample, and according to the different mechanism, the coming out particles or the coming out energy, they will be different. So see, these secondary electrons, these backscattered electrons, these Auger electrons, they are particles, means they are direct electrons. Characteristic X-rays, visible light, Bremsstrahlung X-rays, these are the radiations you are getting. So these are energy waves are there. So we are only concentrated in secondary electrons and backscattered electrons because they are the main particles which will give the idea about our surface of the sample or the inner structure of the material. So we will concentrate it in secondary electrons and backscattered electrons. And when I am telling that secondary electrons and backscattered electrons are important, it means I am talking about scanning electron microscopy. If we see the transmitted light, the partial green light, this one, which is coming out of the sample, it is a direct beam. Maybe it's having some deflection only, or it maybe it had lost some energy. This inelastic scattered electron and elastic scattered electrons. So elastic scattered electrons are very useful in transmission electron microscopy. What is the difference between transmission microscopy and SEM? For transmission microscopy, you need a very thin sample so that the direct light will be able to come out. Sir, you are able to saw the lines I am drawing at the same time?
Yeah, I am.
And for the SEM, you need not to have a very thin sample. Your sample can be thick, doesn't matter. You will get the data, you will get the picture of the surface. But for the TEM, sample preparation is very important. So the TEM can produce very atom resolution images, but the same thing, we have to generate a very good sample. The sample preparation is very important. Moreover, in case of TEM, it's a destructive type technique. So the sample you are making especially for the TEM, you cannot use that sample further for any other thing. And there are some limitations for the TEM that we will talk about when we will talking about the instrumentation. But it can focus very precisely, so you will get a very clear picture about your sample in the atomic limits.
So
these are the limitations which I have talked about already. Yes, sir.
So then we sort of understand the shape, or I don't know, the maybe surface morphology of the sample by the way
Yes,
electrons
if we
scatter.
want to know about the surface morphology, we use SEM technique. It means those
Because you will
electrons.
get, I understand now. Yeah, okay, fine, I understand.
Hmm.
Because in the because in the SEM you will get the electron back
From the
scattered
surface.
towards you.
And when we are talking about the transmission electron microscopy, we can check that which elements are there, what is their proportion, because what happens that as well as their atomic number will increase, their deflection of the beam increases. So according to the deflection, the sharpness of the image, or we say that the contrast will change. According to the contrast, we will get to know that which G number atom is present where.
Okay.
Yes. So these limitations I already talked about. So how fundamental properties of the electrons we are using here? So
And
electrons.
one more question.
Yes.
So
Yes.
and the calibration is already done. So let's say you have zinc, you have iron, for example, atoms. So the
Yes, sir.
diffraction pattern will be different, and they have already calibrated it, and they know that whenever this happens, it has to be zinc. Whenever
Yeah,
this
yes, yes,
happens,
yes.
it has to be iron.
So that's why we say now that when we are talking about the analysis, so if you see the direct picture, you will not be analyze it that much. You can see a picture which is having a very contrasty area, very dark area, but you cannot tell directly that which area is zinc, which area is cobalt, and which area is what. But because you have already some database, the catalog, which know that what is the contrast ratio for which element, then you will use the software and you will get to know that what is the element proportion in your sample.
Okay, got it. Okay.
So electrons have both nature, particle and wave nature, and we can calculate the lambda value if the particles have a particular momentum with that formula lambda is equals to h by p. So if we take the rest mass energy, that is 511 kilo electron volt for the electron. And when we are using SEM and TEM, we can fix a voltage difference between the electron gun and the anode. We can accelerate our electron with a particular voltage difference, and that potential will give them kinetic energy, and with that we can calculate the lambda value. But what happens if you are giving them a very high energy? Then you cannot use the classical formula. You will have to consider the relativistic effect. If the energy is more than 100 keV, then you will have to calculate your lambda, including that relativistic part, and then you will calculate the exact lambda value for your electrons which you are using as a source or as a electron beam. What is the difference between the scattering and diffraction? Actually, if you have an object which is non-scattering, or in case of the SEM, if you having a sample which is non-conducting, then it is invisible for the SEM and TEM. So if you are having a sample which is non-conducting, or as a ceramic, or a, what should I say, is some bio sample, then what do? You coat it with a gold coating, very thin layer, and then you make the conducting surface, and then you do the same. Similarly, for the TIM, you also take care of these things. For the TIM, it is very hard to do some materials because you cannot make them very thin. And we need those electrons which do not go very far from the incident beam. It means the angle of the deviation should not be very far away, because I will tell you later, if the deflection is more than 10 degree, it means those electrons are inelastic. It means they have lost a very large amount of energy. It means we don't know how many times they are scattered and how much energy they have already lost when they have came out of the sample and the detector has detected them. So we need those electrons which have not deviated too much from the incident beam. Sorry. So if we see this picture, this is the high energy beam. Those backscattered electrons and secondary electrons, those are close in the deviation angle to the high energy beam. OZ electrons and the these other radiations, they are very far from them. Why? Because they have deflected a lot. They have scattered it from multiple scattering points, and their energy have been decreased. They are inelastic scattering. They have gone through the elastic scattering. So in TEM also and in SEM also, we are more concentrated on the those electrons which are either inelastic scattered or they are very close to the incident beam. So now I want to show you that what is secondary electrons and what is backscattered electron, because again and again I am using that nomenclature. So what is secondary electrons? If this brown color electron is my incident beam, high energy electrons, they are falling on the sample and they are striking out one of the inertial electron, and that electron is coming out of the sample. So one time the scattering has happened, that thing has struck out the sample, is the electron, but that electron further is not losing any energy, it is coming out of the sample. So these electrons are actually secondary electrons which are coming out of the sample. Those electrons are from your sample, they are not the incident beam. Those electrons are giving you the idea about your sample, about your material property. These are the secondary electrons. What are the backscattered electrons? Backscattered electrons are actually same incident beam, but deflected. First they are attracted because of the nucleus, then they are deflected due to the repulsion from the electron cloud. So the backscattered electrons are actually elastic scattered electrons, they haven't gone through any scattering center. They have just deflected back from the nucleus. So that is, these are the back scattered electrons. They give the idea of the deeper regions of the sample. Secondary electrons can give you the idea from the a little bit upper of the region. So now I will show you how the region has been separated out in your sample. So if you see, this is the plum size. This is the plum. This is the actual interaction of your electron in your sample. So I have given the shade of lighter and darker area. So the least area, the lighter area is actually OZ electron. What is OZ electron? OZ electron is actually, imagine the secondary electron is coming out, but before coming out, it will again hit a outer cell electron. That outer cell electron is actually OZ electron. So OZ electron is there. Then the next will be secondary electrons. Then further deeper backscattered electrons, and then there are different radiations are there. Characteristic X-ray, Bamslang, and fluorescent X-rays. Those we are not interested that much. Now there are so many different characteristics which we need to know when we are going to know about our instrument and as well as the what is happening just above the sample. I will explain it very deeper in the next talk, but I will explain what are these things actually. So what is elastic and inelastic scattering? Sorry, I have wrote the same thing. So if my electron beam is striking on the sample, how much energy it is losing, how many centers it is scattering through, that will depend. It's a elastic scattering or inelastic scattering. If they are not losing energy, it means it's a elastic scattering. If they are losing energy, it means it is inelastic scattering. Mean free path means between two scattering points, how much length have one electron has traveled, that is mean free path. Differential cross section and scattering cross section, they are very close. Differential cross section is actually the angle by which one electron is deviating from the middle, means from the incident light beam direction. And scattering cross section is actually a probability cone by which one electron is supposed to scatter when it is very near to the atom. So these are the different characteristics which we need to know when we are going through our instrumentation. Now, when we are talking about scattering, we can either think it like an energy or as a phase. It means electrons have lower energy after scattering, or they have same energy. It means they have gone through elastic scattering or inelastic scattering, or they can be considered according to phase. Some electrons can be in same phase, some electrons can be out of the phase or not in the any relationship between the two electrons. So we can say coherent scattering and incoherent scattering, and elastic scattering and inelastic scattering. So if the
Nikhil,
deflection, yes sir.
when you say coherent and incoherent, so do you consider similar type of electrons? So do you say two Auger or whatever that name was, are electrons have scattered coherently, or do you consider all sorts of electrons and then you
No,
also say,
actually, sir, if we are talking about OZ electron, it is impossible that they are coherent. That
okay,
means near to impossible. If we are
I
taking
just give an
elastic
example.
scattering,
Okay,
uh,
okay, go
so
on.
if we take, I think the next will be that. I will go to that picture, then I will. This picture, if we will see now. So
Mm-hmm.
in transmission type, this coherent and incoherent is matter. So these are elastic scattered electrons now.
Mm-hmm.
We are talking about elastic scattered. They can be only coherent or incoherent. If they are very close to the deviation angle, then they can be coherent. If they will deviate more than 10 degree, then the relationship between the phases is very tough. They will not be in phase mostly. So when we are
Mm-hmm.
talking about elastic scattering beam, na, then we talk about coherence and non-coherent type.
Okay, okay.
So for OZ electrons, it is very difficult that they are coherent.
Mm-hmm.
For anything which is beyond this area, na, it is very hard that they are coherent.
Okay.
Elastic things can only be possible to be coherent.
Or incoherent.
Yeah.
Okay.
So I have written like if When we talk about elastic scattering now, if they are between 1 to 10 degree deflection, then usually they are coherent. But if that angle is more than 10 degree, they become more incoherent. So if we compare with the X-ray, we know that X-ray, when they interact with your sample, they only interact with the electrons of your sample. But if we take the electrons, they can scattered by the electrons also, as well as they can also interact with your nuclei of the material. So they can give you much more information rather than your X-ray diffraction or that dispersive electron X-ray which you can do with your sample. Now, the elastic scattering, if we talk about, mostly why they are so important. First of all, they have not lost energy, so the contrast in the TEM images is very good. Mostly the diffraction pattern, which I will show you later, the diffraction pattern which we use, so they are very dark spot or light spots, they are there, the intensity will be high, so they are easy to identify. For isolated atoms, if you are talking about, then if electron is interacting with the electron cloud, then the angular deviation will be low. But if they are attracting towards the nucleus, then they will be scattered more. Then the diffraction, that cross section will be very large. This is the real image. The first picture is actually a kidney stone. This is the SEM image of the kidney stone, that's the surface area. So it is a very clear-cut picture, and the resolution is only 5 micrometer for 3 centimeter. So if you see, this full image has a real life width of 30 micrometer. Only 30 micrometer it is. And this is my sample, which is 4 mm in the real life dimension. And this is the SEM image, which I have taken in a 10 micrometer magnification. So you can see in the real life, this is polished sample. This is looking like very smooth, but still there are so many scratches. And if I would have shown you the 2 micrometer resolution, you could be able to see the different secondary phases in my sample according to the dark and white area. The patches will be there, and with that help, you can see where secondary phases have deposited and how much area they have. How much area is secondary phase in my sample? You can directly see with the help of SEM image. And if you want the element mapping, or you want the composition of your sample, you can do EDX, the energy dispersive X-ray analysis, and that will give you the exact composition of your sample. If you want to know deeper about electron microscopy, you can go through these two references, and you will get to know very deep knowledge about that. Thank you.
Wow, very good. बहुत अच्छा था.